Good morning. Our today's topic is mapping function in cache memory. That is cache memory mapping. Mapping function in cache memory. Cache memory mapping means how the main memory data will get mapped on the cache memory. And actually, it is not moving. It is copy. That means the data will be remain in the main memory, and also it gets replica will get dumped into the cache memory. So that is what it is doing. In general, there are three different methods are there for performing these mapping functions. Three different methods are there. So one is direct mapping, that is the first one. The next one is set associative mapping, and last one is fully associative mapping. Okay, direct mapping, the cache memory that is used direct mapping technique, we can call it as direct mapped cache. Okay, and the cache memory which use this technique, that is a set associative mapping, that will be set associative cache. And the last one is fully associative cache. Okay, so these are the three methods used for performing this mapping. Okay, mapping means we are copying the data that is present in the main memory to where cache memory. Okay, that is what the memory mapping. Now we can discuss first one, that is direct mapped caching, or direct mapping technique in the cache memory mapping. So before studying about direct mapping technique, consider this example. Here you can see, suppose this is a main memory and this will be the cache memory. Okay. And the main memory, suppose consider the size of the main memory. Here we have taken, it is 4K. 4K memory. 4K memory means how many words will be there in that 4K memory? That means 64 into 1024. Okay. That is equal to 65,536. This much words will be there in the, we can accommodate this much words in this main memory. Okay, here in this main memory, it is divided, we can see that it is divided into number of blocks. Okay, and each block is having a size 16 words. That means we are dividing the main memory, the entire main memory, into number of blocks, and each block contain 16 words. That means how many blocks will be there? Because total size of the main memory is what? This one, 64K. That means 65,536. Okay, so that is divided into 16 words block. That means we can divide that into 16. Okay, then totally we will get how many blocks we will get? 4096. So total number of blocks that is present in the main memory is 4090. That is from block 0 to 4095. Totally in the main memory we will get 4096 blocks. Okay, so that is the division of main memory. Okay, similarly the cache memory also we will divide with 16 words in each block. Here, the size of the cache memory is 2K. 2k means it is equal to what? 2k means what? 2k means 2k means it is 2 into 1024. No, that is equal to what? That is equal to 2048. Okay, so total number of 2048 words can accommodate in this cache. Here, here in this cache memory also we will divide that into equal sized block, and each block is having the size. It is 16 bit because we have already divided this also into 16 words. Okay, the same division here also we need to apply. That means 2048 divided by 16. Okay, so we will get a 128. Okay, so total number of blocks. Okay, here in cache memory we will call each block, we will call it as a cache line. Okay, these blocks we will call it as cache line. Okay, we can call it as cache line or block, whatever. Okay, but generally we will call it as cache line. We will divide the cache into number of lines. Okay, here in this example, then total number of blocks that can accommodate in the cache memory is 128. That means from block 0 to block 127. Okay, now we can see how the memory mapping is happening. Okay, so initial status you already understood. That means here we will divide the main memory into number of blocks. Each block is having the size of 16 words. Okay, so in this example, the block is, total memory size is 64k. So we will get the 4096 blocks in the main memory. Okay, and in this example, the size of the cache memory is 2k. So after the division we will get a 128 lines of cache. That means we will get 128 cache block. That is from block 0 to block 127. Now we can see how the direct mapping is performing in this cache memory. Direct mapping means we need to copy the content from the main memory to where? Cache memory. Then how we will copy? From where to where we will copy the data, the blocks. That is what in direct mapping. Here in direct mapping, we can see each block of main memory maps to only one cache line. That means each block of main memory maps to only one cache line. That means block 0 will maps to cache block 0. Okay, and block 1 will map to cache block 1. Okay, that means block 0 it won't map any other. That is block 0. Block 0 main memory block 0 എവിടെയൊക്കെ map ചെയ്യും? Cache memory block 0 മാത്രം, വേറെ എവിടെയും map ചെയ്യില്ല. Block 1 block 2 ഒന്നും map ചെയ്യില്ല. Okay, so that is what it is. Each block of main memory maps to only one cache. Block 0 will maps to block 0 in the cache. Block 1 will be maps to here. Likewise, block 127 maps to this block 127. Then from next block 128, that will be mapped to block 0. Then block 129, that will be mapped to block 1. Likewise. Okay. Then what block 256, that will be mapped to block 0. That means in the cache memory, block 0 can accommodate either main memory block 0 or main memory block 128 or main memory block 256 or likewise. Okay, so that is the mapping function. Okay, that means the mapping function here we are using is I is equal to j modulo m, where I is the cache line number and j is the main memory block number. Block 0, block 1, likewise. J is the main memory block number and m will be the number of cache lines. Okay, m will be the number of cache lines. Here in this example, it will be 128. Okay, so this is the mapping function here we are using in direct mapping technique. Okay, that is I is equal to J modulo M. That means each block of main memory maps to only one cache line. That means in cache memory block 0, it can accommodate block 0, block 128, or block 256, block 256. These blocks are loaded into their cache block 0. Okay. Similarly, in the cache block 1, it will be loaded into block 1, block 1, and block 129, then block 256. These are stored in the cache block 1. Likewise, okay, for calculating the cache line, we will use this memory in this equation, this mathematical equation. That is, I is equal to J modulo M. Okay, I is equal to J modulo M. This is the equation. But in some case, there may be a situation. Suppose a processor is requesting a block 128. Okay, but here in this cache memory, block 0 is already occupied. And the processor is requesting block 128. Okay, suppose all the remaining cache lines are free. Then also the processor, the cache memory block 0 has to replace it with the 128, because we studied that in direct mapping technique, each block of main memory maps to only one cache line. That is one limitation in this direct mapped cache. Okay, there is one limitation, because if the cache lines are available, then also we need some replacement algorithm to replace this block, because each block will map only to one cache lines. That means at a time cache block 0 ഇവിടെ തന്നെ ഉണ്ട്. Then 128 ആണ് processor request ചെയ്ത് കഴിഞ്ഞാൽ 128 നമുക്ക് എന്ത് ചെയ്യാൻ പറ്റില്ല, വേറെ എവിടെയും അക്കോമഡേറ്റ് ചെയ്യാൻ പറ്റില്ല, ഇവിടെയേ അക്കോമഡേറ്റ് ചെയ്യാൻ പറ്റും. അതുകൊണ്ട് എന്ത് ചെയ്യണം, ഈ 0നെ നമ്മൾ റീപ്ലേസ് ചെയ്തിട്ട് replacement for that we can use different replacement algorithm. Okay, then we need to move that to where 128 here. Okay, so this is what direct mapping technique. Okay, in direct mapping you need to remember the points that each block of main memory maps to only one cache line. Okay, then more than one memory block is mapped into the same position in the cache memory. That may lead to contention, that we have discussed. That may lead to contention for each block, even if the cache is not full. Okay, so to resolve the contention, by allowing a new block to replace the old block. Okay, leading to trivial replacement algorithm. Okay, so this is a mapping function. I is equal to J modulo M, or you can write it like this: I is equal to J modulo M. Okay, then I is the cache line number, J is the main memory block number, M is the number of cache lines present in the cache memory. Okay, so these are the examples. That is cache block 0 can, that means block 0 or block 128, block 256, etc. is loaded in the cache block 0. Similarly, block 1, block 129, 257, and these are stored in the cache block 1. Okay. So in this direct mapping technique, here in this example, there are main memory address is 16-bit main memory address will be there. Okay, you can see here 16-bit main memory address are there. Here the first 4 bits, okay, first 4 bits, that is here in this 4 bits, these bits are required to identify a particular word within the block. Okay, these first 4 bits which are used to identify a particular word within the block, and the remaining that is remaining 12 bits, we will call it as block number of the main memory. Okay, that is these remaining 12 bits. Okay, we will call it as block number in the main memory. Okay. And these block numbers in the main memories are again divided into two sections. Okay. One is called the line. Line means that is cache line. What is cache line? That we already discussed that. In cache memory, we will divide the memory into different blocks, and each block in the cache memory, we will call it as cache line. Okay, each block in the cache memory, we will call it as cache line. Okay, so here the 7 bits in this memory address. Okay, that is, these bits are required to identify the block number in cache memory where a main memory block will be placed. Okay, main memory block will be placed. So that is this cache line. Okay, that means the number of bits required to identify the block number in cache memory where a main memory block will be placed. Okay, block number in the cache memory where a main memory block will be placed. Okay, then last one is the tag bit. Okay, here in this example it is 15. Okay, last one is the tag bit, and in this example it is 50. Sorry, 5. Okay, in this example it is 5. Okay, so this tag bit represent which among the main memory block are reside in this cache memory. Okay, which among the main memory blocks are reside in this cache memory. We studied that in cache block 0, it may be block 0 in the main memory, or it may be block 128 in the main memory, or maybe 256, whatever it is. So that tag bit will identify, that will represent which among the main memory blocks are reside in the cache memory. Okay, so these are the memory address. Here in this example, total size of the memory address is 16-bit. Okay, so that is what I have written here. Address is in 3 part: tag part, and then bits identifying line in cache, and word identifying bits. Words are a number of bits required to identify a particular word within the block. Then the remaining bits, generally it is for block number of the main memory, that is divided into two sections. One is line, number of bits required to identify the block number in cache memory where a main memory block will be placed. Okay, then last bit, tag bit. Okay, that represent which among the main memory block reside in cache memory. Okay, then actually this is a simple and inexpensive technique to implement. Okay, but there are some limitations are there. That is a fixed cache location for any given block. If a program accesses 2 blocks that maps to the same line repeatedly, then what will happen? Cache miss will be very high. Okay, because we studied that in cache memory, each block of memory maps to only one cache line. So if a program accesses 2 blocks and that maps to the same line repeatedly, what will happen? Cache miss will be very high. Okay, so that is what a direct mapping technique. Then next one is set associative mapping. Okay, set associative mapping. This is what set associative mapping. Visible ആണോ ഈ slide? അല്ലേ? Visible അല്ലേ? ആണോ? Okay. Okay. So this is set associative cache or set associative mapping. The mapping technique, which the cache memory, which use this mapping technique, we will call it as set associative cache. Okay. Here in set associative cache, we will group these cache memory blocks into different sets. The block of the cache memories are grouped into sets. Okay, blocks of cache memories are grouped into sets. That may be 2 block set or 4 block set. That depends. Okay. Generally, it will use 2-way or 4-way set associative. Okay. Here in this example, we have used 2-way set associative. because 2 blocks per set. Okay, that is block 0 and block 1, that will be set 0. Then block 2 and block 3, it will be set 1. Then block likewise block 4 and 5, that will be set number 2 likewise. Okay, that is the block of the cache groups. Cache memory lines are cache memories are grouped into set. Okay, and the mapping allow a block of the main memory to reside in any of the specified set. That means while mapping, the cache block 0 can accommodate this, the main memory block 0 can accommodate either of these block position. That means either block 0 or block 1. Okay, that is what a set associative mapping. Okay, അതായത് ഇപ്പം ബ്ലോക്ക് 0 ആണ് നിങ്ങൾ ഇവിടേക്ക് സെറ്റ്, ഈ സെറ്റ് 0-ലാണ് വന്നിട്ടുണ്ടെങ്കിൽ ഈ സെറ്റ് 0-ലുള്ള ഏത് ബ്ലോക്കിൽ വേണേലും എന്ത് ചെയ്യാം, ഇറ്റ് ക്യാൻ ബി അക്കോമഡേറ്റ്. ഓക്കെ, ലൈക്ക് വൈസ് നെക്സ്റ്റ് മെമ്മറിയിൽ ഏത് ബ്ലോക്ക് സെറ്റിലാണോ വന്ന് അതിൽ ആ ബ്ലോക്ക് വിത്തിൻ ദാറ്റ് ബ്ലോക്ക് ഇറ്റ് ക്യാൻ അക്കോമഡേറ്റ് എനിവെയർ. Okay, so that is what a set associative cache. Set associative cache. Here in set associative cache, the block of the caches are grouped into sets, and the mapping allow a block of the main memory to reside in any block of the specified set. Okay, and this is the mapping function that is used in set associative mapping. This is the mapping function that is used in set associative mapping. That is I is equal to J mod V. Okay, where I is the cache set number, that is set 0 or set 1 or set 2 likewise. Okay, I is the cache set number, J is the main memory block number. This, okay, J is the main memory block number, and V is the total number of sets present in this cache memory. Okay, total number of sets present in the cache memory. Okay, and as we discussed that in set associative cache, the set associative cache is generally designed as 2-way set associative or 4-way set associative. In this example, we have used 2-way set associative. Okay, that is, in this case, the cache block, the cache has 2 blocks per set. Okay, cache has 2 blocks per set. That is, the memory block 0, 128, etc. What maps to the cache block, cache set 0. That is, they can occupy either of the 2 block position within that set. Okay, either of the 2 blocks position within that set. So that is set associative cache. Okay, set associative cache. Remember the points that what are all the points we need to remember? Here, blocks of the cache are grouped into set, and mapping allow the block in the memory to reside any block of the specified set. Then this is the mapping function. Okay, this is the mapping function. Here in this example, we have divided this is the memory address, that is first 4 bits. It is used to identify the words. The next 6 bits for set. Then last 6 bits are for tag. Okay, so that is set associative cache. Then last one is fully associative cache memory. Okay, fully associative cache. Here, in fully associative cache memory means any line from main memories are, that is, any block from main memories are, main memory may be placed anywhere in the cache memory. Okay, that means block 0 can place anywhere from 0 to 127, anywhere in the cache memory. So that is fully set associative cache. Okay, in fully set associative cache, any line from main memory may be placed anywhere in the cache. Okay, so the memory address here is interpreted as 2 field, because what that main memory block can place anywhere in the cache memory. So the memory address and that has two field. First 4 bit. Here in this example, it is 16-bit memory address. So first part, that is first 4 bit, which is used to identify the particular word, and the remaining 12 bits are used for tag bit. Okay, that is what here memory address is interpreted as two field, tag and word. Tag and word. Okay, the tag uniquely identify the block of the memory. Tag, it will identify which block of the main memory is reside in the which cache memory. Okay. Therefore, here in this example, in this fully associative cache, what it has to do? All preserved address are searched and compared at the time of responding to the processor's request for the main memory content. Because what in the main memory block, block 0 can be placed anywhere in the main memory, is cache memory. That means when a processor is requesting a particular block, it has to search from block 0 to block 127. Okay, so that will be what it will take time because it has to search all the tags to find out a particular block. So, in order to make the response faster, the search within controller is performed through some hardware mechanism. Then we can improve the searching mechanism in this fully associative cache memory. Okay, so these are the 3 techniques that are used in where we are using these techniques in cache memory mapping. Okay, cache memory mapping. Okay, so cache memory mapping means what? We are copying the content from the main memory to cache memory. Okay, so that is what the cache memory mapping. There are 3 methods are there: direct mapping, set associative mapping, and fully set associative mapping. Okay, these were the 3 methods. In direct mapping, the equation we studied, the set associative mapping. This is the equation: I is equal to j mod v. That means each block we will divide, each cache box are grouped into set. Okay, and this will be the memory mapping function. And the last, fully associative means main memory block can be placed anywhere in the cache line. Okay, anywhere in the cache line. So that is fully associative cache memory. Okay. Then next topic is improving cache performance. How we will improve the cache performance. Okay. So for discussing cache performance, first, we can see the average memory access time in the cache memory. Okay, so this is the equations for finding the average memory access time. Okay, that is average memory access time is equal to hit time plus miss rate into miss penalty. So this is the equation for finding the average memory access time. Okay, that is hit time plus miss rate into miss penalty. Okay, so by analyzing this equation, you can see that how we will improve the performance. So improve the performance means we need to reduce the average memory access time. That is what we are improving the cache performance. Okay, we need to reduce the memory access time. How we can reduce the memory access time? We can reduce the memory access time by reducing heap time, miss rate, and miss penalty. Then we can reduce the average memory access time. So these are the 3 possibilities to reduce or to improve the cache performance. That means to improve the cache performance, generally we can say that we need to reduce the average memory access time. So for reducing average memory access time, we need to reduce the miss rate, we need to reduce the miss penalty, and we need to reduce the heat time. Okay, these are the things that we need to do. We need to reduce miss rate, miss penalty, and hit rate. Then how we will reduce this miss rate, miss penalty, and heat time? That is what we have to do. Okay, how we will reduce this miss penalty and heat time. So for reducing mistrade, what are all the things what we have to do? We can use large cache block. Okay, large block size, large cache size, and higher associativity. Okay, so that will reduce the mistrade. Okay, for reducing mistrade, these are the things that we can do. That means we can use large block size, then large cache size, and higher associativity. Higher associativity means maximum it will be n associative. Suppose if n lines are in the cache memory, we have to use n associative cache memory. Okay. Associativity, we studied that two-way associative, four-way associative. Previous slides we studied. So for reducing that, reduce the mistrade, we can use large block size, large cache size, and higher associativity. So these are the points for reducing mistrade. And to reduce the miss penalty, okay, what are the things we have to do? For reducing miss penalty, we can use multi-level caching, giving priority to read over. Okay, so these are the two things that we can perform to reduce the miss penalty. That is, either we can use multi-level cache. Multi-level cache means what? Multi-level cache means there are different levels of cache we have discussed in the memory hierarchy. L1, L2, L3, likewise. Okay. In that, in those manner, for reducing miss penalty, we can use this multi-level cache. Okay. And also giving priority to read over write. Okay. So these are the two things that we can perform for reducing the miss penalty. Then last one is reducing the heat time. Okay, so for reducing heat time, we can avoid the address translation by indexing the caching. Okay, so these are the things that we need to perform for improving cache performance. Now we can see what is this large block size and all in detail. Okay. So as we discussed that use of large block size will increase the improve the cache performance. That means increasing block size that will help to reduce the miss rate. Then it will improve the cache performance. Okay, that is larger blocks also reduce compulsory misses. Okay, because larger blocks can take better advantages of spatial locality. Okay, larger block can take better advantages of spatial locality. Okay, but there are some drawbacks out there for using this larger block size. Okay, it improves the cache performance by reducing the miss rate, but there are some drawbacks. These are the drawbacks. Okay, that is the miss penalty will increase as it is required to transfer larger block size. Okay, since the number of cache blocks are decreased, the number of conflicts miss and even capacity miss can increase, because if you use larger block cache block means number of block size will be decreased, number of blocks will be decreases, cache blocks will be decreases, isn't it? Then the number of conflicts miss and even capacity miss can increase. And another drawback is that the overhead may outweigh the gain. Okay, so these are some of the drawbacks when we use larger block size for improving the cache memory performance. Okay, then next one goes first larger block size, then larger cache size. Okay, that is use larger cache memory. Okay, so that will also increase the size of, that is increasing the size of the cache is a straightforward way to reduce the capacity misses. Okay, for by using this large cache memory, there are also some drawbacks are also there. That is, it will increase the heat time, since the number of tags to be searched in parallel will be possibly larger. Okay, then that result in higher cost and power consumption. Okay, So that is the drawbacks for using large cache memory. Okay. So using large cache memory, it will improve the performance of the cache memory. The next one was we can use higher associativity. Okay, that will also improve the performance, cache performance. So for n-way associative cache, the miss rate reduce as we increase n. Okay, and also reduce conflict misses as there are more choices to place a block in the cache memory. Because if you are using large block, large associative is there are more choices are there in a particular set, isn't it? So that will reduce the conflict misses. Okay. But there are some drawbacks are also there in this higher associative. By using higher associative cache, that is increase the hit time as we have to search a larger associative memory, and also increase the power consumption due to higher complexity of associative memory. Okay. Then next is use of multi-level cache. That will also improve the cache memory. Okay, multi-level cache, that means level 1, level 2, level 3. Likewise, if you use multi-level cache, it will improve the performance. Okay, that means multi-level cache is one of the technique to improve cache performance by reducing the miss penalty. The L1 cache can be small enough to match the clock cycle time of the fast processor, and the L2 cache can be large enough to capture many access that would go to main memory, thereby reducing the miss penalty. Okay, so by using this multi-level cache, we can reduce the miss penalty. So we can improve the cache performance. By reducing miss penalty, it will improve the cache performance. Then next one is giving priority to read miss over writes. Okay, that is the presence of write buffer can complicate the memory access. That means the buffer may holding the updated value of a location needed on a read miss. Okay, then but it will simply wait for the buffer to empty. Okay, that might increase the miss penalty. So for in order to overcome that, what it has to do, check the write buffer by write buffer content before reading. Okay, if there is no conflict, let the memory access can continue. So that is what the giving priority to read miss over writes. Okay, so that will also helps to improve the cache performance. Then another method is that avoiding address translation during cache indexing. So for that we can use some virtual address. Okay, so that will helps to improve the cache performance. That means even a small and a simple cache must go with the translation of virtual address to physical address to access memory. So in order to make it faster, we use virtual address for cache. Okay, so by using this virtual address for cache, we can avoid the address translation during cache index, address translation time during the cancellation, because hits are much more common than misses. Okay, so such cases are termed as virtual caches. Okay, so by using virtual caches, we can avoid the address translation during cache indexing. So that will improve the cache performance. Okay. Then some other additional optimization techniques for improving cache performance are these are some other additional technique, that is use of small and simple first level cache to reduce the hit time, wave prediction to reduce the hit time, pipelined caches and cache access to increase the cache bandwidth, multi-band caches to increase the cache bandwidth, critical word first and early restart to reduce the miss penalty, compiler optimization to reduce the miss rate, prefetching of instruction and data to reduce miss penalty or miss rate. These are some additional optimization techniques. Okay, you just to remember these terms. Okay, so these are all the technique for improving cache performance. Mainly, you need to remember these three points by reducing miss rate, reducing miss penalty, and reducing hit rate. Okay. Then how we will reduce the miss rate? By using larger block size or larger cache size or higher asset associativity, then reduce mispenalty. You can use multi-level cache or giving priority to read override, and reduce heat time. We can avoid for that we can avoid the address translation when indexing the cache. So for that we can use virtual cache. Okay, so these are the different technique. Okay, ഇനി നമുക്ക് ബാക്കി അടുത്ത ക്ലാസ്സിൽ നോക്കാം. നിങ്ങളുടെ അറ്റൻഡൻസ് ടൈപ്പ് ചെയ്തു. അക്ഷയ്, റോഷ്നി, അശ്വിൻ, അനുശ്രീ, വിഷ്ണു പ്രകാശ്, അഷ്ന, ഡൊമിനിക്, ആദിൽ, വൈഷ്ണവ്, അഞ്ജന. ഓക്കെ, ഇത്രയും പേരാണുള്ളത് അല്ലേ? അപ്പോൾ നമുക്ക് അടുത്ത ക്ലാസ്സിൽ കാണാം. താങ്ക് യു.